Introduction to Quantum Information Processing. Welcome to Lecture 20. In this lecture, I will explain a phenomenon called nonlocality, which is a strange kind of behavior that quantum systems can exhibit. This behavior can be explained in terms of games played by a team of cooperating players. The players must individually answer certain questions, and they must do this without communicating between each other. The lack of communication appears to restrict what the players can achieve. However, with quantum information, strange behaviors can occur that defy what one might intuitively think is possible. First of all, let's note that entangled states cannot be used to communicate instantaneously. What I mean by this is the following. Suppose that Alice has a quantum system in her lab and Bob has a quantum system in his lab, and the two labs are in physically separate locations. Alice and Bob's systems might be in an entangled state, for example, one of the Bell states. Then there is no quantum operation that Alice can perform on her system alone whose effect is detectable by Bob. If Alice wants to communicate with Bob, she has to send something to him. To see why this is so, consider the density matrix of Bob's system. That is, the density matrix that results when Alice's system is traced out. If Alice performs a unitary operation or measurement on her system, then this has no effect on the density matrix of Bob's system. So any kind of measurement that Bob performs on his system will have exactly the same outcome whether or not Alice performs the operation. And this is not specific to two systems. If there are three or more parties, then the same thing holds. Operations on one system have no detectable effect on the other systems. Now let's consider a three-player game commonly referred to as the GHZ game, named after its inventors, Greenberger, Horn, and Zeilinger. Let's call the three players Alice, Bob, and Carol. This game works as follows. Each player receives a 1-bit input. Call the respective input bits R, S, and T. And each player is required to produce a 1-bit output. Call the respective output bits A, B, and C. The rules of the game are the following. First, it is promised that the input bits R, S, and T have an even number of ones among them. In other words, R XOR S XOR T is 0. So there are actually three cases of inputs, 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. Second, there is no communication allowed between Alice, Bob, and Carol once the game starts and their inputs have been received. So, for example, although Alice will know what her input R is, she does not know what S and T are. The third rule defines the winning conditions of the output bits. The three players win the game if the XOR of their output bits is equal to the logical OR of their three input bits. This is just a condensed way of describing this table. There are four possible cases of inputs, 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And for the first case, the XOR of the outputs should be 0 for the players to win. For the other three cases, the XOR of the outputs should be 1 for the players to win. To get a feeling for this game, here is an example of a strategy that Alice, Bob, and Carol could use. Alice could just output her input bit. She receives R as input, and for this strategy, she produces R as output. Bob could output the logical negation of his input bit. He receives S as input and produces the negation of S as output. And Carol always outputs 1, regardless of the input she receives. So how well does this particular strategy perform? Here I've added the output bits arising from the strategy to the table. You can see that the first output bit A is R, the second output bit B is the negation of S, and the third output bit C is always 1. Consider the first case of inputs 0, 0, 0. There the XOR of the output bits should be 0. And it is 0. So they win in this case. For the second case, the XOR of the output bits should be 1. And it is. So they win in this case too. They also win in the third case. So far so good. But what happens in the fourth case? In that case, the XOR should be 1. But the output bits have XOR 0. So they lose in that case. This is an example of a strategy, and this strategy wins in 3 out of the 4 cases. Is there a better strategy that wins in all 4 cases? Call a strategy that wins in every case a perfect strategy. Let's see if we can find a perfect strategy for this game. Alice's output bit is a function of her input bit. Let A0 denote her output bit if her input bit is 0. And let A1 denote her output bit if her input bit is 1. Similarly, define B0 and B1 as Bob's output bits in the 2 cases, and C0 and C1 as Carol's output bits in the 2 cases. So we have 6 bits specifying a strategy. We can express the winning conditions in terms of these 4 equations. The first equation says that when all 3 input bits are 0, the XOR of the output should be 0. The second equation says that when the input bits are 0, 1, 1, the XOR of the output bits should be 1, and so on. So to find a perfect strategy, we just have to solve the system of equations. Is there a solution? In fact, there is no solution to this system of equations. These are linear equations in Mod 2 arithmetic. Suppose we add the 4 equations. On the left side we get 0, because each variable appears exactly twice. They cancel each other out. On the right side we get the XOR of 3 1s, which is 1. So summing the equations yields 0 equals 1, a contradiction. It's possible to satisfy any 3 of the 4 equations, but not all 4. Therefore, there does not exist a perfect deterministic strategy. I say deterministic because this analysis doesn't consider the case of probabilistic strategies. Could there exist a probabilistic perfect strategy? There cannot exist a probabilistic perfect strategy either. This is because a probabilistic strategy is essentially a probability distribution over all the deterministic strategies. And the success probability is a weighted average of all the success probabilities of the deterministic strategies, weighted by the probabilities. If the questions R, S, and T were selected randomly, with probability 1/4 for each possible input, then the success probability for every deterministic strategy would be at most 3/4. So the weighted average for any probability distribution on deterministic strategies cannot be higher than that. Okay, suppose you actually carried out this game with Alice, Bob, and Carol. You generate a random triple of questions and check whether their answers win or not. If you just play this game once, then they might win by luck. In fact, they can win with probability 3/4. What if you play 4 rounds, once for each of the 4 input possibilities? Will the players necessarily fail in at least one of those rounds? No, not necessarily. Note that the players might use a different deterministic strategy at each round. Their strategy can satisfy any 3 of the 4 equations, and they can arrange to have a different equation violated for each round. In fact, the players can ensure that they win each round with probability 3/4. So they would win any 4 rounds with probability 3/4 to the power 4, which is slightly more than 30%. On the other hand, it's highly unlikely that the players would be lucky enough to win, say, 500 rounds. That success probability is 3/4 to the power 500, which is less than 1 over a trillion, 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 trillion. So if you did play the game for a large number of rounds, with randomly selected questions at each round, and the players won every single time, what would you make of that? What makes the game non-trivial is that the players cannot communicate with each other. If they could communicate, then there would be an easy perfect strategy. For example, suppose that Bob sent his input bit S to Alice. Then Alice knows R and S, and she can also deduce T because of the condition that the parity of all 3 bits is promised to be 0. So Alice knows which of the 4 cases they're in. A winning strategy is for Alice to just output the required parity to win, and Bob and Carol to output 0. This wins in all 4 cases. And there are ways of scrambling up the outputs that obscure this pattern, so that Bob and Carol do not always output 0, and yet the 3 players always win. So how can we ensure that they do not communicate? Maybe they each have a very well-concealed transmitter. You could ensure that there's a significant distance between the players. Here I'm depicting them on separate planets. And also time their inputs and outputs tightly so that they cannot communicate fast enough for the messages to reach each other before their deadlines for producing their outputs. For this, we assume that they cannot send signals faster than the speed of light. In physics terminology, we are making the input-output events space-like separated. Then, assuming that the theory of relativity is correct, we can be sure that they are not communicating their inputs to each other. But what if this is done and they still keep on winning for every round? If the players had quantum systems that were entangled, could that possibly help? Recall that entanglement does not enable communication. There is no way that Bob can perform an operation on his system that can be detected by Alice. So, is there any possible way that Alice, Bob, and Carol could keep on winning this game? If you're not already familiar with scenarios like this, then I recommend that you pause the video now and think this over. The answer will come at the next slide. The answer is yes, there is a way that they can always win, and I will show you how. They do use entanglement. Let them share this 3-qubit state. Alice possesses the first qubit, Bob possesses the second qubit, and Carol possesses the third qubit. First, I'll explain what the players do with this entanglement. What Alice does is she looks at her classical bit R. If that bit is 1, she applies a Hadamard transform. Otherwise, she does nothing. Then she measures her qubit in the computational basis and outputs the outcome of the measurement. Bob and Carol act similarly. They check their input bit. If it is 1, then they apply a Hadamard. Then they measure in the computational basis. Now, let's see how this strategy performs. There are 4 cases of inputs. Let's begin by considering the first case, where R, S, and T are all 0. In that case, neither player applies a Hadamard transform, therefore they measure the above state in the computational basis. The result will be the string in one of the kets. It will be 0, 0, 0 with probability a quarter, 0, 1, 1 with probability a quarter, 1, 0, 1 with probability a quarter, and 1, 1, 0 with probability a quarter. For all 4 possibilities, the parity is 0, which is what it's supposed to be for the 0, 0, 0 case. Now let's consider the case where RST is the string 0, 1, 1. In that case, Bob and Carol apply Hadamard operations, and Alice does nothing. It's straightforward to check that those 2 Hadamards change the state to this, and if this is measured in the computational basis, the result will be a random 3-bit string with parity 1. So their strategy works in this case too. The case where RST is 101 and 110, those cases are similar to the previous case due to the symmetry of the situation. So this strategy works in those cases too. That's how Alice, Bob, and Carol can win with probability 1. If they play several rounds of the game, then they set up several copies of the above entangled state, 1 copy for each round. So, how is this entangled strategy working? Is it somehow communicating? If you look at the outcome distributions for the various cases, you can see that each individual output is an unbiased random bit. So the result of Alice's measurement contains no information about Bob and Carol's inputs, and similarly for the other players. In fact, it can be shown that any perfect strategy using entanglement must have the property that each output by itself is a random unbiased bit. In fact, even if we consider pairs of output bits, they are uncorrelated random bits too. It's only the tripartite correlations among the 3 output bits that contain information about the inputs. Let's summarize this G8Z game. It's a game played by a team of 3 cooperating players who cannot communicate with each other once the game starts. Any classical team can succeed with probability at most 3/4. Allowing the players to communicate would enable them to boost their success probability to 1. Entanglement cannot be used to communicate. Nevertheless, entanglement is another way that the players can boost their success probability to 1, but not by using entanglement to communicate. Instead, entanglement enables the measurement outcomes to be correlated in ways that are impossible with classical information. Now, you might wonder why I showed you a 3-player game. Are there 2-player games for which the same phenomena occurs? I showed you a 3-player game because it's the simplest game that I'm aware of that illustrates the point. Here's an example of a 2-player game that exhibits the same type of property. It's commonly called the magic square game, and a good way of understanding it is to first consider the following puzzle. Imagine a 3x3 matrix whose entries are filled in with bits. Can you find values for the bits such that the number of 1s in every row is even, and the number of 1s in every column is odd? Please pause to think about how to do this. You may have come to the realization that it is impossible to do this. Why? Consider the number of ones among all of the 9 bits. The row condition implies that there are an even number of ones in total. The column condition implies that there are an odd number of ones in total. And this is a contradiction. Now keep this in mind while I describe a 2-player game. Alice and Bob are collaborating and cannot communicate with each other once the game starts. Alice and Bob each receive a trit as input and are each required to return 3 bits as output. Think of Alice's input as a row of the matrix. Think of Bob's input as a column of the matrix. The winning conditions are: first, Alice's 3-bit output has even parity. Think of these as the bits of one of the rows of the matrix. Bob's 3-bit output has odd parity. Think of these as the bits of one of the columns of the matrix. And the third condition is a consistency condition. Where Alice's row intersects Bob's column, the bits must be the same. For example, if Alice was queried the second row and Bob was queried the third column, then Alice's 3rd bit must be the same as Bob's 2nd bit. What can we say about this game? It turns out that there is no perfect classical strategy for this game. Of the 9 possible questions, Alice and Bob's strategy must fail for one of them. The maximum success probability attainable is 8/9. The proof of this is based on the fact that there is no way to fill the bits of the table that satisfy the parity conditions. But there is a perfect strategy that uses 2 Bell states as entanglement. It's an interesting strategy, but I won't go into the details of it here. So the Magic Square game is a 2-party game that exhibits the same kind of property that the GAZ game exhibits with 3 parties. So far, you might think that these games are weird curiosities that have no conceivable application. But these games can be useful for enforcing certain types of behavior in cryptographic protocols. A simple example of this involves devices for generating random bits. Suppose that you purchased such a device that purportedly generated a stream of random bits. How could you know that this is a good device? You could open the box and see if the internal mechanism looks legitimate. But even if superficially it looks like some process that you think is generating randomness, it's possible that it's a fake random generator and that the manufacturer was trying to trick you. What the manufacturer could do is produce a long sequence of random bits in the factory and store those random bits in 2 memory devices, and hide one of those memory devices somewhere in the box and keep the other memory. And what the device could actually be doing is just outputting the bits stored in that memory device. Note that the output would look like random bits to you, but the manufacturer would have a copy of those bits. They would know exactly what the next output bit is going to be. If you use such a fake random generator in a cryptographic context, for example to generate a random secret key, that could be trouble. The manufacturer would know the key. Unfortunately, in the context of classical information, there is no remedy for this, even in principle. If you don't trust the manufacturer of your devices, then there's no way that you can be sure that it's really generating random bits that are unknown to the manufacturer. But with quantum devices, it's possible to certify the randomness of untrusted devices. The device would actually consist of 2 components. that contain entangled quantum systems. You physically separate the two components and input a short random seed into each component. From this, each component outputs a long string of bits. You check if the inputs and outputs satisfy a certain function called a test. If they pass the test, and if the input-output events are space-like separated, then you know for sure that the outputs are really random bits. I'm not claiming that such a system is practical to implement for wide usage, at least not these days. But this shows that, in principle, it's possible to actually certify randomness using quantum information, something that's impossible even in principle with classical information. Non-local games also have profound implications in the foundations of physics, which will be the topic of the next lecture. Okay, let's end this lecture now.